For decades, our entire understanding of the cosmos has relied on the lambda cold dark matter model. Lambda CDM is a framework that argues the universe is dominated by slow-moving, invisible particles that gradually clump together under their own gravity. As these dark matter structures grow, they pull in regular matter, the hydrogen and helium gas, eventually forming the first generation of small stars. Because this dark matter moves so sluggishly, the model dictates a strict speed limit for cosmic construction. Those first small stars have to spend billions of years crashing into each other and merging before they can form massive structures. According to the math, massive galaxies simply cannot exist in the earliest chapters of cosmic history. That timeline remained solid until the James Webb Space Telescope opened its mirrors and looked further back in time than any previous instrument. Staring into the deep past, just 300 to 600 million years after the Big Bang, astronomers spotted two baffling types of objects. They found blue monsters, massive, extremely bright galaxies, and little red dots, which appear to be supermassive black holes already active in the early universe. Finding objects this massive at such an early stage forces a choice between two realities. Either our standard model of the universe is incorrect, or our understanding of early astrophysics, how gas actually turns into stars, is missing a massive piece of the puzzle. Discovering these mature structures so close to the Big Bang is like digging through Precambrian rock and finding a fossilized rabbit. The timeline is reversed, creating a choice between a cosmological crisis or a bizarre astrophysical anomaly. To understand the depth of this problem, researchers had to prove these galaxies were truly ancient, rather than nearby faint objects playing tricks on the telescope. The proof lies in cosmic redshifting. As light travels across the universe, the literal physical expansion of space pulls on the light, stretching the light wave into longer, redder wavelengths. Over billions of years, visible light stretches so far that it shifts entirely into the infrared. Webb captures this light using infrared spectroscopy, which reads the specific signature of the ancient stretched light. By measuring how much the wavelengths have shifted, astronomers can calculate exactly how long the light has been traveling through space. Within this data, scientists search for the Lyman break, a specific abrupt cutoff in the light spectrum. This occurs because neutral hydrogen floating between galaxies absorbs light at a specific energy level. The further the light travels, the more that break shifts into the infrared. This Lyman break acts as an undeniable DNA test for the light. It confirms the glow from these galaxies traveled for over 13.4 billion years, locking in the timeline and proving these impossible structures are real. With the distance verified, researchers began picking apart the specific anomalies within these ancient galaxies, starting with the deeply colored little red dots. Spectroscopic data from these dots reveals broad emission lines, thick bands of light that indicate gas swirling at extreme velocities, paired with unusually weak X-ray signatures. These signatures identify the dots as supermassive black holes forming in a window of time where we previously expected only small, isolated stars. Normal black holes form when a star collapses, but these giants appear too early for that process. This points toward direct collapse black holes, where primordial gas clouds crush straight into black holes without forming stars first, or dark stars, hypothetical giants powered by annihilating dark matter. There is a secondary chemical problem, the presence of heavy elements like nitrogen. Nitrogen is typically produced by low-mass stars over billions of years. Seeing it so early suggests a hyperactive environment where chemical maturation happened almost instantly. These maturation rates show the early universe was not a slow evolving gas cloud. Instead, it was a dense, active environment where black holes likely formed before the galaxies that hosted them. To track how quickly this growth happened, scientists are observing the epoch of reionization, the transition from a dark, opaque universe to the transparent one we see today. After the Big Bang, the universe was filled with a thick fog of neutral hydrogen, but the first hot stars emitted massive amounts of ultraviolet light, burning away this fog into transparent bubbles that eventually merged to clear the cosmos. We can measure this clearing through the patchy KSZ effect. As electrons are freed inside these bubbles, they Doppler shift the light of the cosmic microwave background, the oldest light in the universe, changing its temperature in specific spots. By mapping this patchy temperature shift, scientists can determine exactly how fast these early galaxies ionized their surroundings, providing a second clock for the cosmic dawn. The standard Lambda CDM model remains incredibly resilient at explaining the large-scale universe, but our local astrophysics rules regarding early star formation clearly require a rewrite. The definitive answer between a cosmology update and an astrophysics update will likely come from upcoming detectors like the Simons Observatory. If these new detectors see increased lensing, where background light is heavily bent by the gravity of invisible structures, it proves there was more dark matter present in the early universe than we expected. This would require a fundamental update to our laws of physics. But if we see normal levels of lensing alongside a changed patchy KSC signal, the dark matter model survives. In that case, the physics of the universe is fine, but our models for how gas turns into galaxies are what need to be rewritten. These universe-breaking galaxies reveal the chaotic, unbalanced, true beginning of the cosmos, a frantic era where black holes briefly ran ahead of their host galaxies before settling into the stable universe we inhabit today.